Hello, welcome back to Cinderella Math. In today's video, we're going to be doing a just kind of basic introduction to exponents and also roots, mostly square roots. I might go into cube roots, but yeah, I would say this is suitable for middle school, anywhere in middle school, or if you're in high school and you just need a review of these topics, that's great too. All right, so we're going to get started with just some basics of exponents. All right, I have a little bit of terminology I'd like to share with you. Okay. So let's say we have 3 to the 5th power. The number that is written normal size, that is known as your base. Now that's not always a number. You can also have a letter there, but for now, the 3 is our base. And then the guy that's written higher and it's a little bit smaller, that is your exponent, also known as your power. So you can call it either. Same difference, okay? And that's really all the vocabulary. What does this mean? Exponents represent repeated multiplication. Okay, so what does this mean? On this example, 3 to the 5th power means to do 3 5 times, multiplied with itself 5 times. So that's 3 5 times. There we go. And then you'd multiply all that together, either by hand or in a calculator. You know, that's going to depend on your teacher, what they let you do there. By hand, I usually go like that. So that's 9. That's 9. So that's 81 times 3 is 243. So 3 to the 5th can be evaluated as 243. Now, we don't always have to evaluate them. That might not be the goal, but oftentimes it is. So the long way that I wrote this here, this is called expanded form because it's long, right? Expanded means make it longer. That's expanded form. And this one, the original here, is exponent or exponential form. I'm a very bad speller. Here we go, exponential form. There we go. And this one's expanded. All right, let's do a couple more. So now I'm going to start with the expanded form. So I'm going to do 6 times 6 times 6. And now let's put that into exponent form. You're doing 6 3 times. So you can say this is 6 to the 3rd power. And 3rd power, you can also say cubed. And that will make more sense here in a second when I talk about perfect squares and perfect cubes. Okay, can we mix the numbers like this? Can I do 2 times 2 times 2 times 2 times 3 times 3 times 3? Yes. That would be 2, 1, 2, 3, 4 times to the 4th times 3, 1, 2, 3, cubed, or to the 3rd power. So I'm not actually evaluating. I'm not figuring out what the final answer is there. I'm just converting it from that long expanded form into the exponent form. And you can also, once you get up into algebra, or maybe you already are in algebra, you'll see this a lot with letters. So that's x, 1, 2, 3, 4, 5 times, so to the 5th power. Y, you can put a times or not. You can just run it together to the 2nd power. And 2nd power, we often say the word squared. That'll make sense in a second. And that's really all there is to it. On a calculator, you usually have an exponent button and it looks like this. That symbol is called a caret. So, and that's how you spell it, I'm pretty sure. Caret with a K. And that is the symbol for exponent. So if I was doing 6 to the 3rd power or 6 cubed in the calculator, most calculators, now refer to your own calculator for this, but most calculators I would hit 6, that weird caret button, and then 3, and then equals. And then it should tell you from there. Okay, that's kind of the basics. There's a trick with the powers of 10 real fast, I'll show you. If you do 10 to the first, anything to the first power, by the way, is just itself. So 10 to the first is 10. Side note, if it's like 3 to the first, it's 3. If it's a half to the first, it's a half. If it's x to the first, it's x. So anything to the first is itself. Now back over to the tens. 10 squared, that's 10 times 10, that's 100. 10 cubed, that's 10 times 10 times 10, that's 1,000. You're probably picking up on the trick by now. 10 to the fourth, 10,000. However many your exponent is, that's how many zeros. That had 1 0. 10 squared, 2 zeros. 10 cubed, 3 zeros. 10 to the fourth, 4 zeros. So that's just a trick there that you can do with tens. All right. And now specific exponents that we use. Oops, wrong thing. Oh my goodness. Did not realize I had those old slides on there. There we go. Specific exponents that we use a lot are squares and cubes. So square, when you hear that word, that is something to the second power. So you can say x to the second power, or you can say x squared. So this would be 3 squared, 10 squared, 99 squared. So anything to the second power, we usually say squared. Why? All right, so let me draw a square here. You learned back in elementary school, and if you're in middle school, you've learned this in your middle school geometry, that a square is the same all the way around. And we use tick marks to show that. So if this side is 3, so is this, so is this, so is this on a square, right? Right? And a little bit of geometry here. When I ask for the area of this square, you would do length times width. Length times width. Or you could call that base times height. Same difference. That would be 3 times 3, which is 9. But 3 times 3 we could write as 3 squared. Let me do that again. And 9, that number, the answer, is referred to as a perfect square. We like perfect squares. They make life easier in high school math. Perfect square. Okay, let me do that again. Let's build another square. And again, it's the same all the way around. So I'll say the length this time is 5, the width is 5, or base and height. So if I were to ask for the area, you would say length times width, or base times height, is 5 times 5, which you could rewrite as 5 squared. And 5 times 5 is 25. So that number, 25, is a perfect square. Okay, so that's why the second power, we speak the word squared. So the first rectangle, or excuse me, square represented 3 square, and the second one represented 5 square. And then the answer of that, 9 and 25, those are 2 examples of perfect squares. If you're ever not sure if something's a perfect square, here's what you can do. So let's say 9. We know this is going to be a perfect square. You pretend you're building with Legos or like square crackers, and you could take 9 square crackers. Now, this isn't going to be beautiful because I don't have, pretend. That makes a square, right? It's not perfect, I know, but it's 3 rows, 3 columns. That's a square. 9 is a perfect square. Take 10 crackers or Legos, all the same size, all squares, and this will not work. You cannot build a square with 10 crackers or Legos, whatever you've got there. So there's 9, and then as soon as I add the 10th, it's not a square anymore. So this is not a perfect square. Now, once you get to like huge numbers, um, it's not as easy to visualize with the Legos or crackers, like 144. That is a perfect square because that's 12 times 12, which could be rewritten as 12 squared. So this is where it's really important to know your times tables from elementary school. They have the perfect squares on them up through 12, right? So if you think about your times table, I'm not going to write the whole thing, don't worry. The diagonal of the times table is where your perfect squares are. Now there's more than that, but those are the first several. 1 times 1 is 1, that's a perfect square. 2 times 2 is 4, perfect square. 3 times 3 is 9, perfect square. And if you just keep going diagonal, 16, 25, 36, 49, 64, 81, 100, all down the diagonal of a standard times table. Those are your perfect squares. And again, there's more, but if you know your times tables, you at least know the first several perfect squares. All right, cubes. Let's talk about perfect cubes. These don't come up as often. The squares, I would say, are more important, but the cubes are nice to know. Square is more important. Cube's nice. All right. So again, I mentioned earlier that if it's anything to the third power, we could say x to the third power, and that is fine. That is totally correct. But we often say that this is x, or whatever the base is, cubed. That's what we'll also often say for third power. So second power, we say squared. Third power, we usually say cubed. Why? Where did that come from? So again, this is from geometry. When you have a cube, so you can think of like a cube of sugar, if you have a cube tissue box, not all tissue boxes are cubes, but some of them, Amazon box in a perfect cube, a Rubik's cube, something like that. Okay, so a cube is just a 3D square. And when you find the area of this, it's length times width times height. So length times width times height. So let's say those are all 2. So it's a square, it's all squares, so they have to be all the same. So let's say this is 2, 2, 2. So that would be 2 times 2 times 2. Better known as, in exponential form, 2 to the third, or 2 cubed. That's where the cube comes from. Okay? Which is 2 times 2 is 4, times 2 is 8. So 8, that answer is known as a perfect, not a perfect square this time, but a perfect cube. And again, these don't come up quite as often as the squares, but they're still kind of fun. Now, these are not on the times table. I mean, there are some on there, but they're not like a pretty pattern. Like the squares were straight down the diagonal. You won't see that with the cubes. Okay, I'll just do one more example here. Let me draw another cube, and then we're going to go on to roots, and then that's it for this video. Okay, so there's our cube. Let's say this is 5, 5, 5. So when I want to find not the area, I think I put the wrong thing on the last one, the volume, so the space inside. Sorry, I think I misspoke on the last slide. The volume is length times width times height. So that would be 5 times 5 times 5, which in exponent form would be 5 cubed. So there's where's the word cubed come from? And 5 times 5 times 5 is 125, and that is a perfect cube. Okay. Right? If you're ever wondering if a number is a perfect cube, here's how I would do it. So we know 125 is. I would grab my calculator, if you're allowed to use one, and start dividing that up. So that divides into 5 times 25, and then 25 is 5 times 5. So see how there's 3 5s? That's how you know it's a perfect cube. So let me do one that's not. Let me do 40. So if you divide that up, that's what? 4 times 8. And then that's 4 times 2. So that's 2 4s and a 2. So you need 3 of them. So no. If this was 4 4 4, it would have worked. So this is not a perfect cube. That's how you can tell. And you can do that trick with squares too. So let's say, is 30 a perfect square? Break that up. 3 times 10. If there's 2 that match, it's good. Nope. You could also do 6 times 5. Do those match? No. 30 is not a perfect square. But try 64. 8 times 8. They match. 64 is a perfect square. If you could have a square, 8, 8. That works. But you could not make a square out of 30 crackers or Legos or whatever blocks. All right. And then the opposite of taking powers is taking roots. And I'm mostly going to be focused here on square roots. So we've had squares, right? 3 square, 5 square, 10 square, x square, and so forth. So again, that means 3 times 3, 5 times 5, 10 times 10, x times x, right? So this is the squares. This is expanded. What's the opposite of that? So you know math, pretty much everything has an opposite. Adding and subtracting, opposites. Multiply, divide, opposite. So what's the opposite of doing a power, specifically doing a second power or a square? The opposite is called square root, and the symbol is this. You can call that either the square root symbol, or you could also call it the radical symbol. Either way, probably if you're in middle school, you're going to stick to the root word for that. All right. And what does it do? So let me say square root 25. They're saying we have a square. The area is 25. What is the sides? Well, what times itself is 25? 5 times 5. So the answer, one of the sides, you just write it once, is 5. So this is the reverse of 5 squared is 25. Those are opposite operations there. Okay, let me show that again. So if I say, oh gosh, 7 squared is 49. The reverse or the opposite operation is square root. That's how you say that when you see that symbol. Square root 49 is 7. Okay, so if they say square root 16, that means there is a square. You don't actually have to draw this. I'm just illustrating here. The area is 16. And you know it's a square, so the length and the width have to match. What times itself is 16? 4 times 4. So this is 4. Don't write it twice, just 4. The end. Okay. Now, if you know negative numbers, this does get a little different, but for today, I'm just sticking with positives. So those are square roots. Now, not all numbers come out pretty. So let's say we have the square root of 7. This is not pretty. You can put that in your calculator and it will be crazy. It'll be an irrational number. So if you do put that in the calculator, that's going to be 2.64 ... It keeps on going. So not all square roots come out nice. Because if you think about it, if you have a square, what times what would give you an area of 7? Well, you could do 7 times 1, but then it's not a square. That would be a rectangle, right? If it was 7 times 1. You cannot think of a whole number that works. You cannot make a square out of 7 Cheez-Its. There's 6 and there's 7. It's just not going to work. I could try it this way. There's 2, 4, 6, 7. It is, you cannot make a square out of 7. So that's why the answer is crazy. It will not be a pretty or a whole number. Okay. And that happens a lot. Usually your teacher or your worksheet will tell you what to round to. So usually I'll say round to the 10th. So this 4 would not bump. And I would say this is 2.6. But just follow your teacher or your worksheet. Sometimes they'll say 10th. Sometimes they'll say 100th. If you're in high school math, you may not round at all. You might just leave it as a root. Middle school, you probably will round. All right, just real fast, what about cube? If there's square roots, can there be cube roots? Yes, there can. And this same symbol, but it will have a little 3. Okay, and let me put 8 right there. So that means there's some cube out there, and they've already taken the volume. Again, sorry for misspeaking a couple slides back. And the volume again is length times width times height, and that came out as 8. But we know this is the same as this and as this. So what times itself is 8. So question mark times question mark times question mark is 8. That would be 2 times 2 times 2 is 8. So this answer is 2. Just write it once. Okay? That's how you do a cube root. And again, those don't come up near as often as square roots, but they do come up, especially in high school math. You might see those. Not everything is a perfect cube. If I would have put 9 in there, this wouldn't have worked. Because you could not figure that out. We can do 3 times 3 is 9. So you could do 3 times 3 times 1, but then it wouldn't be a cube anymore. It would be a rectangular prism, but they want a cube. So nope. So you can put this in a calculator. Most calculators have a cube root button. Especially if you're in high school, you have a cube root button. But you'll get an answer, but it'll be an irrational. So not all roots come out pretty, and that's okay. Again, if it's ugly, your teacher or your worksheet or whatever will tell you what to round to. Right? Alrighty. So this was just a very basic introduction. Oops, that's definitely the wrong lesson. On square roots, perfect squares, perfect cubes, and just kind of an intro to exponents. I hope this was helpful, and I hope to see you back here soon. Let me know if you have any questions. Bye-bye.